Well, welcome to Counting Methods. Topic one starts us off with something very, very useful. It is called our fundamental counting principle. This is going to be kind of the cornerstone, the foundation of everything we do in this unit. Essentially, all we're trying to do in this unit is try to figure out the universe of some sort of situation. Universe is our fancy way of saying all possible outcomes. How many are there? How many are there is going to be the thing that we don't know. And we can come up with, we can say how many passwords there are, how many different phone numbers, how many different arrangements, how many different combinations. And we give you all these different puzzles. But effectively, there's only one question that we're asking. How many different things are there? What are all the possible outcomes of whatever scenario we kind of concoct? And we're looking for shortcuts. We're looking for very, very efficient ways to kind of do this. And so at the very, very core, right at the beginning, we have to kind of make a distinction between the way that we would use the word and the way that we would use the word or. And this kind of comes, there's a connection to set theory in a way. And was our intersection word, or was our union word. But for our purposes, we really do pick on the word and in so many of these questions. And it is always permission for us to multiply. Multiply, multiply, multiply. There are a handful of questions. Actually, some of the more tricky questions in this unit would kind of use the word or, which is always going to give us our permission to add. And fundamentally, these are our two operations for the fundamental counting principle. So to kind of show this, we could kind of create some smaller scenarios here. How many 4-digit ATM PIN codes are there? How secure is your bank card if you only have a 4-digit PIN? And it's a pretty vague question, but this is a very, very useful way of showing the fundamental counting principle. Now, in theory, if I was to try to list all of the outcomes, that this is just going to get outrageous. There's just so many. But I could start listing them off. Someone's PIN could be this, and then maybe this, and then this, and then eventually maybe this is someone's PIN, and this is someone's PIN, and all the way up, and all the way up to maybe the highest PIN I could think of, 9999, and this is a very, very long list. And we would ask, well, how many are there? Could you count them? Could you predict how many there are? And this strategy would be pretty useless in a way, just to kind of start writing out every possible PIN number you could ever think of, because maybe some of these questions have answers in the thousands, millions, tens of millions, and I mean you could sit there for weeks writing out every various PIN that you could kind of come up with. So we start coming up with some ideas here. The fundamental counting principle plays on patterns and plays on options. And we can break down each digit. And we always ask the same kind of question each time. We would always kind of ask, how many options? If you don't like the word options, how many choices are allowed? for this spot. And in a 4-digit one, we could ask this question 4 times. I would kind of ask this question in my head: how many things are allowed to be here? And we can show this work. I mean, if you think about what how many digits there are to pick from, all the options that could be here are 0, 1, 2, 3, 4, 5, or 6, or 7, or 8, or 9. Those are the numbers. So when you're picking a bank pin, these are your options. And it's not like you're picking all of them. You're picking one of these numbers, but that's not what we're writing here. We're not writing that you're only picking one. That's not what the fundamental counting principle wants us to kind of sort out. It wants us to figure out, the quote unquote, the total, the universe of this. So how many options are there at the moment? There are 10 options. And then I would ask that question again and again and again. Now I'm not down to 9 options, because as you can see, it doesn't matter if you pick the same number twice. I mean, this literally could be someone's PIN number 0000 or 6666. Like, this depends. There's no rules on PIN numbers. This gives us many more options. And so we would go best say here again, like, well, there's still 10 options. It's still the same digits. There's 10 options. There's 10 options. And when you're picking a PIN number, you would be picking one of these digits and then another digit, and then, another digit, and then another digit. And you could kind of pick a pin because you're picking one and then a second and then a third and then a fourth, and then you've created a 4-digit combination. And so multiplying is permitted and is the correct operation. And when we start multiplying these out, we would get an answer that's quite big. And so that there are 10,000 PIN codes in this kind of scenario. And that would be the universe. That would be all possible outcomes. And this eventually, what we're going to say in our next unit is that the probability of guessing someone's PIN code would be 1 in 10,000, because on the bottom of a probability is the total. It is the universe. And this is what we're going to spend this unit doing: always knowing the universe in any situation. And the fundamental counting principle, that is exactly the strategy that I have used here. The fundamental counting principle allows us to multiply choices and options by more choices, by more choices, by more choices. Sometimes options are taken away, sometimes extra options are given, but we can use our multiplication. And is usually the connector in a lot of these questions. Is just logically the way that we're connecting a chain of events. And so we get to multiply a lot, and we can multiply and multiply, and it makes a really nice strategy. I mean, this strategy is not meant to be complicated. It is a really, really hands-on, approachable strategy for almost this entire unit. Honestly, we can use this for almost every single question that we have to throw your way. And so let me take a look at another example. Let me say that there are. Let's talk about a phone number. I changed my mind. I'm kidding. Let's talk about 8 people. And let's arrange them for a photo. I could create a couple questions about this. How many different photos in total? And B, how many of those photos will have Sam, who is a specific person and, one of those 8 people, standing first. There's a very, very specific spot for Sam. And we can ask this, and this is a classic fundamental counting principle kind of question. And I would use this exact kind of same strategy. So setting up my counting principle, I would be going spot by spot, person by person, and every single part of the way I would be saying, well, how many people can be here? And then how many people are left and can be here? And the logic that we have to use is to go a little bit past this idea. There's a little bit of a breakdown of logic here if you think that there's 8 people and that all 8 people could be in any position. So there must be 8 options for every single position. But this does not really hold once you start looking at it. Let me create 8 people here. 5, 6, 7, 8. And here are my 8 people. I'll just put some letters to represent those 8 people. I got Sam and a couple other people. Now, yes, there are 8 people who can stand in this spot. But once somebody has been delegated and chosen to stand there, there is no way that this person could stand in more than one spot at the same time. Maybe in a different arrangement, this person could be in the second spot or in the third or in some other spot. But in any given arrangement, once somebody has been chosen, well, there are 8 choices. Only one of them is being picked. But once this person has been picked, there would be no situation where you still have 8 options. We read the fundamental counting principle kind of happens in an order. I mean, we go place by place. We pick somebody, and then we pick something else. And then we pick a third person. And then, and we get to multiply all these numbers. But because this number no longer makes sense, because there's not 8 people again who are still available, who are still allowed to stand there. And so we start naturally running down, start running out of people. We start counting down through this progression here. And so there would only be 7 people left at that time. And then if someone else was decided to stand there, I'm only down to 6. And then I'm only down to 5 and 4 and 3 and 2 and 1. And in very, very specific situations, like when you have people, I mean, you can't use the same person twice. That's just assumed. It doesn't have to say that anywhere because it's people. It's not like building a code out of digits on an ATM machine. I mean, when you pick 0, why can't you pick 0 again? It's not like it's a person, it's not an object. I mean, it was allowed to use the same number twice or all 4 times. But in this case, it's just naturally you lose a person when you kind of arrange them in a very specific order and in order, perhaps. And we get this natural countdown. And you got to watch out for these countdowns. They're going to happen quite a bit in questions where you start running out of things and not everybody is available after you've already used a couple of people. And so as I say, do this countdown, I would get, whoa, that's a typo. There we go. I would get an answer that's known as 40,320. And we can make very, very specific requests at this point. How many of those photos have Sam standing first? And we start introducing a little bit of these very specific requests. We call them restrictions. And it immediately means that we don't have 8 people who are allowed to be there. This is Sam's spot. Let me even write out what we would call our sample space. It's very, very handy to keep track of people, to keep track of your choices, to make a little set and use it so that you don't ever lose track of things. And so I do see 8 people, but 8 people aren't allowed to be here because I made a very specific statement about Sam has to be standing first. And so this is Sam's spot. There is only one Sam. I mean, that's kind of a given here. And so what we would say is that there's only one choice. There's not 8 choices. There's only one allowed person in that spot. And we do these first. We really do want to lock down these restrictions. You don't want to put Sam somewhere else, or at least allow Sam to stand somewhere else, and then all of a sudden you don't have any Sam anymore, and that gets really, really awkward and confusing. You really do want to focus in on these restrictions first. Make sure that you've allowed who needs to be there. And then, Sam can't be picked again. I mean, Sam's supposed to be there. He can't be picked again. And then we have a few options left. And I'm down to 7 people. So that's why I would say there's only 7 people who are allowed to be here. This does not mean we're picking all 7 people to be here. It means that currently there are 7 options available. As in, there would be a 1 in 7 chance of you being picked to stand next to Sam. 1 in 7 chance, because only one person is being picked out of the total 7 that are available. And we say that there are 7 options available. And the counting principle, the fundamental counting principle, gives us a really nice shortcut, a really nice way to come up with these answers without sitting there trying to figure out every possible variation. Now, once somebody is picked, then we're down to 6, down to 5, down to 4 and 3 and 2, and then the last person. And in this scenario, this would multiply out. Remember, we're multiplying. We're picking Sam and then another person, and then. All of these connections logically mean and multiply. And there would be 5,040 different photos possible where Sam was specifically chosen to stand first. And this is a really, really handy strategy. And we're going to have a ton of practice with it. And I hope this has helped.